Hi, this is Jipeng coming from the University of Electronic Science and Technology of China. I am going to present our teacher-student networks with multiple decoders, a novel method for solving math word problems. Typically, a math word problem is composed of a problem description text, a solution expression and a final answer. An example is shown in the figure below. It is worth noting that this problem has multiple solutions. In general, most math word problems should have multiple solutions. At least, mathematical law can be applied to get different solutions for a single problem. Well, with such training examples, math word problem solvers should have two goals, that is, objectives to optimize: the generation loss of answer and the loss of solution expression generation. As a matter of fact, most existing approaches use only the latter objective, since it is easier to implement and consistent with translation-style methods, which are proved to have superior performance in most sequence generation tasks. More exactly, these methods are based on the deep generative network composed by encoder-decoder architecture. The encoder encodes the problem text into latent embedding, and later these latent embeddings are fed into the decoder to generate the solution generation. This is similar to translating problem text into equations, which share the manner with machine translation and speech recognition. As is shown here, they deploy a single decoder and fit to the only solution expression given on datasets. It is, therefore, hard for them to generate diverse but equivalent solution expressions, limiting the generalization ability to various cases. More importantly, as there may exist multiple solution expressions and only one correct answer, this solution generation objective tends to give wrong penalty to correct solutions which are different from annotation 1. However, the more reasonable goal should be generating the correct answer. In order to address the limitations of the previous training methods, we suggest to consider these 2 points. First, how to regularize the training procedure so that the training can be guided under a better goal. Second, how to increase the diversity of generation. So, we proposed a TSNMD method. The key modifications are these 2 items: solution expression. Previous models will falsely penalize these correct solutions as the training objective only fits the fixed solution expression. For example, the label solution expression of the problem here is 200 minus 12 times 10 and then divide 20, although 200 divide 20 minus 12 times 10 divide 20 is also a correct solution expression and can compute the right answer. The previous training objective will undoubtedly penalize this kind of generation results. A simplest solution is to improve solution annotations and add extra training examples. However, the current datasets all only give the single solution expression annotation. Here, we choose to pre-train the teacher network to guide the learning behavior of the student network with the same training data. The intuition is that the teacher model observed through all solutions, including those with equivalent solution expressions under mathematical laws. Therefore, it gains the knowledge of regularizing the learning behaviors of the student network. More intuitively, when a student predicts an equivalent solution expression to the ground truth but causes an undesirable loss, the teacher network will help to amend this mistake by giving soft labels. More exactly, as this teacher-student learning manner has nothing to do with model structure, both the teacher model and student model follow the architecture of a previous sequence to tree methods, GTS, which achieved the previous best performance. Second, in order to encourage high-diversity predictions, that is, solution expressions, from the student network, we made some modifications on model structures. In total, we use multiple decoders instead of a single decoder. This multi-head design naturally incorporates diversity in the architecture both during training and inference. Besides, aiming at getting different outputs from different decoders, we try to feed latent variables to different decoders. More specifically, one decoder behaves in the same manner as the previous model and the other one, which shares the structure with the former decoder, has its input embedding perturbed by a Gaussian noise. Also, in order to encourage different decoders to generate different results, we introduce the diverse regularization item and separate beam search here. We added a diversity regularization item and separate beam search to encourage different decoders to generate different results. When it comes to inference, separate beam search is executed per mixture component. It is worth noticing that the solver can only output one solution expression. Therefore, we vote to get the output solution expression according to the prediction score given by different decoders. Here is the overview of our model architecture. Next, I will describe the details of the completed version of the model. The teacher network is trained in prior with baseline architectures, GTS. After that, the student network is fed with the problem text X to generate intermediate embedding H1 is copied from H and H2 is computed by perturbing H with Gaussian noise. Then, they are fed to tree decoder 1 and tree decoder 2, respectively, which output solution expressions Y1 and Y2. In the meantime, the teacher network outputs a soft prediction Y_teacher for the same instance. Finally, ground truth is used to compare with generated expressions and calculate various losses. We conduct experiments in Math 23K and MAWPS. For Math 23K, we evaluated in both training test division and 5-fold cross-validation manner. We can observe from the table below that our model outperforms all the previous methods in all settings. Another important experiment is to investigate the accuracy of solution expression prediction. More accurately, if the predicted solution expression exactly matches the annotated solution, we consider it a positive example. Here, we can compute the number of alternative solutions that each model can provide, which can partly tell the degree of diversity of a model. It can be observed that the accuracy of solution expression generation is lower than the final accuracy of problem solving. This reflects that these MWP solvers have spontaneously learned to adapt to the situation that a certain problem may have multiple solutions. Besides, we investigate the effects from different modules. The results of different word problem solver variants on Math 23K are shown in the table below. Taking GTS as the base model, we try to verify the effectiveness of proposed techniques. First, we evaluate the vanilla teacher-student network by removing multiple decoder structures. The results show that the teacher-student network contributes a lot to improve the performance. Next, we observe that it is beneficial to use multiple decoders. Using 2 decoders with diversity regularization items, the accuracy improved by approximately 0.6%. We also notice that it is necessary to include the diversity regularization techniques. We ablate the regulation item both for the full model and the model with only multiple decoders structure. The results in the table show performance degradation to different extents. In addition, we have verified that GTS plus teacher-student learning plus multi-decoder and GTS plus teacher-student learning in the table solve different parts of MWPs while sharing accuracy. It is not fair to infer that multi-decoder is unnecessary from this comparison. Compared with a single decoder, the model can get more different solutions with multiple decoders. In this case, diversity regularization items can have larger influence. Therefore, although the impact on the multiple decoders without a teacher-student network is relatively small, the influence on the full model is large. At last, we present several generation examples sampled from the Math 23K dataset in this table. In the first example, the problem is asking the proportion of the fired ones. However, GTS falsely predicts the solution expression to compute the proportion of the remaining members and decoder 1 gets the same error. Our model gives the right solution with the help of decoder 2 exploring one more possibility. For the second case, GTS generates a new solution different from the ground truth. 2 decoders also give diverse correct solutions. For the third case, there are key words in the problem text like quotient and remainder while the solution actually needs times and plus. This case asks for a model to handle the confusing descriptions. Our model can better deal with this situation. In summary, we propose a novel approach: teacher-student networks with multiple decoders to tackle the MWP problems. The key components in our approach, that is, teacher-student regularization and multiple decoders in the student network, are validated to be of high effectiveness. The new state-of-the-art results are achieved on the Math 23K and MAWPS benchmarks. Furthermore, our approach is easy to plug in other MWP solvers. We will keep exploring the possibility of making this method a general technique for math word problem solving. Many thanks to your attention and interest. Feel free to contact me if you have some further questions.